Yeah, now I'm going to discuss about this packing efficiency in solid state, that is CBSE Class 12. Yes, before going to what is the packing efficiency of different types of lattices, let's understand what is this packing efficiency definition first. So packing efficiency is nothing but, yeah, now if I take this unit cell, yes, that is a simple cubic unit cell I'm taking. Yes. Let me take this unit cell and then, yes, if I take, for example, this unit cell that is a cube I'm taking here, whatever may be the whatever may be the constituent particles arranged in whatever way the constituent particles are arranged, that means atoms, molecules, or ions, there is always a free space in this unit cell which is present in the form of voids. Voids are nothing but the empty spaces. So this packing efficiency is nothing but the percentage of the total space which is occupied by the particles. So it's defined as a percentage of the space occupied by the constituent particles packed inside the lattice. So in order to know the packing efficiency, how well it is packed in this. So how these atoms which are in the shape of the spheres are occupied in the unit cell. So then we can calculate this packing efficiency of different types of lattices. Let's take this simple cubic lattice. We know that in the simple cubic lattice, in this particular case, the atoms here are present only at the corners here, right? The atoms here are present only at the corners. That means 8 atoms are present at the 8 corners of this lattice, of this cube. So if I show you this one of a simple cubic lattice, these 8 atoms are arranged, right? So here 2, 3, 4, 5, 6, 7, and 8. So if I take the edge, that means the edge, this HA edge, we know that atoms are present at the corners here. And these two atoms or spheres are touching each other. If I take this edge as A here, that A is equal to touching, since these two atoms are touching each other, this is the radius of one atom and this is the radius of one atom. That's half of this molecule, that's half the diameter, and I'm taking half of this, which is nothing but the radius here. So A is equal to 2R, right? Now A is equal to 2R. Now we know that the volume of a cubic unit cell is equal to, what is the volume of an cube here? Same thing we'll take, A cube, right? So all the sides are equal. So A cube, so 2R whole cube, which is nothing but 8R cube. Yes. Now we also know that the packing efficiency, it is given by the formula, packing efficiency is equal to volume of one atom divided by volume of cubic unit cell into 100%. Since we want this as percentage, multiply with 100, so we'll get in percentage. We know that volume of one atom is equal to 4 by 3 pi r cube. We know this formula, so I'll write here volume of an atom is equal to 4 by 3 pi r cube, and volume of unit cell is equal to, of a cube is A cube, nothing but A cube, we already know 4 by 3 pi r cube by A cube is 2R whole cube, which is nothing but 4 by 3 pi r cube by 8R cube into 100, right? So 4 by 3 into 8 into pi r cube into 100. So it is nothing but 0.14 by 6 into 100. When you calculate this, you'll get this as 52.4%, right? So the packing efficiency, how well this cubic lattice, that means the simple cubic lattice is packed, is only 52.4%. So even though 8 atoms are present in this, the packing efficiency is only 52.4%. Now let's calculate the packing efficiency in CCP or face-centered cubic structure. Yes, in order to know the packing efficiency of this, let's understand first what is face diagonal. So first take this face diagonal, the diagonal which is passing uh, uh, this touching the two corners along the faces, along with the face is nothing but the face diagonal. So this AC is the face diagonal here, right? So face C is the face diagonal which is equal to B. I'm representing this as B here. So this is a right angle triangle, right? Right. So if you know this hypotenuse, B square is equal to, that is AC square is equal to AD square plus DC square, right? So I'm taking each edge as A here. Since all of them are equal, I can take anything to be A here. So B square is equal to A square plus A square, right? So B square is equal to 2A square. If I take this B here, root of 2 into A. Right now, if you know this along this face diagonal, the three atoms or spheres are touching each other, right? So the in the face centered cubic lattice, whether the atoms are present at the corners. I'm not representing the at the corners here. 1, 2, 3, 4, 5, 6, 7, 8, and also at the center of the faces, right? So I'm taking only one sphere at the center of this face and the two spheres at the corners, which I'm in needed of. Okay. So this is the face diagonal. Now this face diagonal B is equal to, if I say this is 2R, right? R and R. And this is 1R, half of the diameter. And this is 1R. So totally R plus R plus R plus R is equal to 4R. Right? Now, if I substitute B here, 4R is equal to root of 2A. Right? Now, R is equal to root of 2A by 4. Right? This is R. Or I can write A is equal to 4R by root 2, which is nothing but if I divide and multiply with root 2 into root 2, which is nothing but 4 into root 2 by 2R, right? So which is nothing but 2 root 2R. A is equal to 2 root 2R. And also I can write it as R is equal to A by 2 root 2. Yes, now we know that the volume here is equal to packing efficiency is nothing but, we know the formula, right? Volume of 4 atoms here, because we know that in FCC, what is the total number of atoms per unit cell? It is 4, right? Because we have the atoms at the centers of these spaces. We have 4 atoms per unit cell. So we have taking volume of 4 atoms by volume of unit cell into 100. Right? So volume of 4 atoms will be 4 into 4 by 3 pi r cube, because for each atom it's 4 by 3 pi r cube. Volume of unit cell will be A cube. Here A cube is nothing but 4 by 3 pi r cube by 2 root 2 r whole cube into 100. So after simplifying this, we'll get this to be 74%. So the packing efficiency of Yes, when you calculate, you can get that the packing efficiency CP structure is 74%. Right, this is of FCC or CCP, and HCP also will get the same packing efficiency, that is 74%. Right, for HCP also will get this. And when we look at this packing efficiency of body centered cubic lattice, that BCC, let's take the body diagonal of this. So this is the body diagonal, that means that touching the two corners of this cube diagonally. This is what is called as a body diagonal. So this is body diagonal in this case is nothing but BD here, right? Which is nothing but, again, these three atoms are touching each other, right? Touching each other. If I take this as one radius and this R and R and this R. So again, BD is equal to 4R, right? BD is equal to 4R here. And how many number of atoms per unit cell of this in BCC is equal to, we know that it is only 2 atoms. Right, now let's calculate the packing efficiency now. Right, if I take this triangle here, I'm taking here, if I calculate here, I'll get this as in this triangle I'm taking here. Suppose I'm taking this to be, yeah, we know now here this BD is equal to 4R, which is nothing but body diagonal, right? Which is nothing but body diagonal here. Then if I calculate this one, if I take this as C here, this C is equal to, this triangle here, A square plus this FD. This FD is already calculated from this triangle as 2A square. So now this C square is equal to 3A square, right? So now C is equal to root of 3 into A. So now this is nothing but, if I take this to be, this is 4R, right? So this C is 4R is equal to root 3A. So from this, we know that now 4R is equal to root 3A. Now I can write for A and R as A is 4R by root 3, or R is equal to root 3 by 4 into A. Now we know the packing efficiency formula already. Packing efficiency is equal to, here I said that the volume, volume of two spheres, because two atoms are present per unit cell in BCC, in body centered cubic lattice, and volume occupied by two spheres by volume of, total volume of unit cell into 100. So volume of two spheres is nothing but 2 into 4 by 3 pi r cube into 100 by total volume, we know that is A cube, which is nothing but 8 by 3 pi r cube into 100 by A cube is, we are taking this to be A cube here, right? 4 r 4 by root 3 r of whole cube. All right. When you calculate, or when you simplify this, we'll get this to be 68%. So this is how the packing efficiency of this body centric cubic lattice is derived. Right. Now, if you see the packing efficiency in different types of lattices, for primitive or simple cubic unit cell, it is packing efficiency in simple cubic unit cell is 52.4%. In FCC or CCP and also HCP, we have it as 74%. And for BCC, that is body centered cubic lattice, it was calculated to be 68%. So this is how we derive at the packing efficiency of different types of lattices.